Welcome to another MathCast. In this episode, we're going to be taking a look at how to calculate arc length of a curve. We're going to be looking at the arc length integral formula and just doing sort of a simple example to get us used to working with the types of integrals that you'll be calculating in this section. As we start, we're looking at a curve here, 1/3 x squared plus 2 raised to the 3 halves, and we're looking at it from x equal to 0 to x equal to 3. Now, let me just quickly remind you of our arc length formula. Arc length formula says that the arc length of a curve is the integral of this ds element. And if you remember, the ds element is the square root of dx squared plus dy squared. Now, if we're doing a problem like this where I have y written as a function of x, then the most appropriate form that this integral should take would be factoring out a dx, so that I have dy dx squared in here and then a dx on the outside. Remember, this is the arc length formula in the case where you have y written as a function of x. So for this particular example, my function y is 1/3 x squared plus 2 raised to the 3 halves power. And so I'm told the interval of integration is from x equal to 0 to x equal to 3, so it's basically the length of this curve from x equal to 0 to x equal to 3. It's this length here. And we should expect the arc length to be given to us by the integral from 0 to 3 of the square root of 1 plus, now notice the formula requires us to find the derivative. So if I come off to the side over here and look at dy dx, dy dx is 3 halves times 1/3 x squared plus 2, and I'm going to subtract 1 from the power, and then I have chain rule to worry about, so I have to multiply by a 2x. In doing so, we get a lot of cancellations to occur, and so the derivative in this case is x times x squared plus 2 raised to the 1/2. And so if we go in and write the derivative in now, we'll have x squared plus 2 to the 1/2, all of that squared. And we're integrating with respect to x. So at this point the integral's set up. Let's go ahead and work it out a little bit and see what we can come up with. This is the integral from 0 to 3 of, if I square this inside piece, I wind up with a nice polynomial inside the radical. Which hopefully you'll recognize as being something that we can perfectly factor. If I look at x to the 4th plus 2x squared plus 1, that factors perfectly into x squared plus 1 quantity square. This is a perfect square. And it turns out that in order for a lot of these problems to be easy to integrate by hand, we're going to have to be working with things that wind up being perfect squares. Otherwise, I'm probably just going to ask you to set up the integral but not evaluate it. Alright, if I carry on with the work here, this will be the integral from 0 to 3 then of the square root of this perfect square, which as you can see will simplify nicely for us. And just performing the final integration step here, we should come up with our answer. Evaluating the 3 in here, that'll give us 9 plus 3 should be 12. So the length of this curve is 12 units. Now, units is sort of a general term. We could be talking about length in meters or centimeters or something like that if we were doing an applied problem, but just 12 units of length in this particular example. Now, the only difference in this problem and another problem that we might try to work would be if I took the dx and instead wrote it in terms of dy. Then I could integrate a function that's written as x as a function of y. And we've talked about that in class. It would just be the difference between thinking vertically versus thinking horizontally. And so you also have to be aware of how to integrate in that case for arc length also. Alright, we're going to look at a couple more arc length videos coming up, including some polar arc length and parametric arc length problems. So make sure you take a look at those. Thank you for watching.